All right, guys, welcome to another episode of CUDA Education. Today we are continuing our investigation of ray tracing reflections. So this algorithm basically deals with um, mirror-like objects, right? So we're reflecting things, and this is our default application as it stands. We have a teapot tea dispenser, um, and we have some solid spheres, and we have some mirrored spheres, right? And the teapot is also mirrored. Now, it is my understanding that basically how these mirrored things work, it's not really a texture as such. It's more just it's done within the closest hit shader. So it's done within the shader, and basically what it's logic that says whatever ray comes to me, calculate the normal and spit back out the same ray. So whatever ray I receive, spit back out, return the same ray. Obviously calculating normals and all that stuff. Um, that's sort of how this mirrored thing works. Okay. So sort of had a little insight into that. Um, if we go into the so first of all, we're in the ray tracing reflections piece of the equation. Remember, we have our shaders, we have our GLSL, and we have the closest hit, right? So we have our shaders, and then this is the closest hit. Now, this is the basic logic of the shader. Haven't fully investigated everything in it. But as far as my discussion for today, um, I'm more I'm more concerned with the reflective objects, right? So how do we get these reflective objects, right? What is the procedure to get these reflective objects, right? Um, right. All right. So what's the logic behind these reflective objects here? That's kind of where I just want to start, just to catch my bearings and everything. So there's a whole lot of logic. Notice this is the hit logic. So when this triggers when a ray hits something. So we shoot out rays and then we hit something, right? There's a bunch of stuff: ray payload, color distance, normal, reflector, right? Um, need to dive into this stuff more. But what my attention has, for now, my attention is captured with. Notice how we have normals here. So normal is very important because you have to calculate the normal and all that stuff. Um, unpack the vertices is the size of. Yeah. Okay, so you have to calculate the normal, basic lighting. Okay, objects with full white vertex color are treated as reflectors. Um, so there's some binary logic basically that says if the natural object of the if the natural color of the object is white, then we're going to change that object from being white to a reflector, and it's being controlled by this flag right here, 1.0f or 0.0f, right? So as it stands right now, when we run our application, generally speaking, This is a white object. Let me get my bearings. Where am I? Right, this is a white object, this is a white object, and this is a white object, right? And we could sort of we could sort of prove it by, if we turn off the reflectors, we should, now remember guys, we have to do, whenever we change the shaders, we have to compile to get back into to get back into spare V format, right? So every time we change a shader, remember the shaders are external files, so we have to get it to spare V format in order to have whatever instructions we have in our shader reflected. So this is just my investigation of reflectors. I initially thought it was a texture, but it's actually not a texture. It's just instructions in the hit shader, as you could see here, that basically says if we have a white object, you turn it to a reflector. So as we can see here, we now have white objects, right? For our sphere, for sphere here, and for our T dispenser, okay? So again, we'll just revert it back to that. We have to recompile, and then we get our reflectors back. So again, the reflector basically, whatever ray it receives, it pushes back to you, right? That's what the reflector is. Now we want to do some sort of modifications to this, just to really see what's happening, and really to see this max recursion, the power of this max recursion. So right now, if we run our thing, we get back our application as we expect, right? So this is our application, no problem, right? We get back our application. No problem. All right, so what we want to do is, let's say we make everything a mirror. So we want everything in our scene to be a mirror, right? So if we want everything in our scene to be a mirror, we update our shader so that, and of course I have to compile again. We update our shader so that everything, regardless, you see this is an if statement. So if R is 1, G is 1, and B is 1, then we have a flag of 1 for the ray payload dot reflector. But we're gonna just do indiscriminately. We're not gonna make any. We don't care what the object color is. We're just gonna make everything a mirror, right? And we're gonna see exactly how the application behaves now when everything is a mirror. Okay. Okay, I think I'm good. So when everything is a mirror, now we get something like this. All right, so now everything is a mirror, including, you see our floor is also a mirror. Okay, now basically the only thing that then is shown is the sky model I guess the blue tint of the floor, the slight blue tint of the floor. Tri-model blue tint of the floor. And then we have these black patches. But we know where these black patches come from. We have a full understanding of where these black patches come from, right? You guys know exactly where these black patches come from. This is a result of us running out of the number of reflections we're allowing. So you reflect one time, you reflect twice, you reflect off of the teacup, but then you reflect the reflection of the sphere off of the teacup, and then you reflect the reflection of the sphere of the teacup of the this, you know, and you drill down further and further and further into into as many recursions as you want. Generally speaking, the more recursions that you have, the more complex your scene is, and maybe your frame rate will go down. But that doesn't necessarily flesh out for here. I mean, I don't know. You see we're at 119, 120 frames per second, but it doesn't necessarily flesh out with the way, you know, that logic holds. Maybe there's something I'm missing with that. But as you can see, the reflection of the reflection of the reflection going the fifth time, you're going to see these black spots. Okay. Now we are at 4 recursions in. Okay, so we're here, we're at 4 recursions in. Okay, so as you can see, we have our application and we have 4 recursions in, right? Four reflections in. Okay, let us play with this. So if I lower the number of reflections, what do you expect to happen in our application? If I lower the number of recursions, what do you expect to happen? Quick, this is an easy question. If I lower the number of recursions and everything is mirrored, I expect to see more black spots, right? Because now I have refused to you know, to proceed with more reflections. So there's going to be more spaces where nothing shows because I've halted reflections, right? So I'll go back to 4. I'll go back to 4 and we shall see what happens. So C4 is a little bit cleaner. As you can see, 4 is a little bit cleaner. As we get down to 3, you see it's more pronounced, right? More things are blotted out and the blots are bigger, right? If we go down to 2, what do you think is going to happen? If we go down to 2, what do you think is going to happen? We're only allowing 2 reflections. See, bigger and bigger, blotted out. The reflection of the reflection is this. All this stuff is blotted out now, right? If we go down to 1, everything is blotted out. I mean, at least all our objects is blotted out. I'm sorry, all our objects is blotted out. If I go down to 0, I don't see anything. I have a blank screen. Okay, that makes sense because I'm not reflecting anything, not even the sky. All right, so let's just count back up. So we're at 1 now. We'll do this real quick. We get back our sky, right? We get back our sky. Let's do 2. We get more details. Let's do 3. We get more details. Let's do 4. We get more details, less blotted out stuff. Now let's go in the opposite direction. Let's go to 5. What's going to happen if we increase the amount of recursions? What's going to happen if we increase the amount of recursions? We get less and less spots, blotted out spots, right? So we're at 5. We're going to do 6. See, we're getting a cleaner and cleaner. We're at less black spots. 7. 8. So yeah, we're really cleaning up stuff, right? As you can see. 9. And then let's do 10. So as you can see, as we allow more recursions, things clean up. Now let us see what number we could use to get rid of, see, we're getting a clean image now. Pretty clean. All right, let's do 15. Let's see what happens with 15. All right. All right, we still have our little friend down here. What's going on with our little friend down here? Say hello to my little friend. Let's do 25. We still get our little friend. But as you can see, it's a lot cleaner now. It's like glass. It's actually pretty cool. Right? But we still have our little friend there. But it's a teapot, the reflection of the teapot 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 all the way down. So I think what happens is just that you're basically just trying to, it's still there, but it's just that we can't see it. It's still there, it's just that we can't see it because it's such a small thing. If we do 35, we might still be able to see a dot. Do we see a dot? No, we don't see. Oh yeah, we do see a dot. So you see, this is like 35 teapots down, if you will, or whatever, right? So if we do 30, the dot should be a little bit bigger, right? So you see it's bigger, it's getting bigger, right? And that makes sense. So as you can see, the dot is getting bigger, right? Everything else is pretty cleaned up, but this guy is getting bigger, right? And of course, if we just go back down to our default of 4, you're gonna see that we get all our friends. We have many friends, guys. We have many friends. Look at all our friends. Anyway, all right. So this is what the deal is. But again, we're gonna go back to we're gonna take the reflector thing, and we're gonna only do it for the items that have been deemed as white. We have to recompile our shaders. You guys know about this stuff already, right? We have to recompile our shaders because we have to get this. This is an external file. We have to get it into sphere V format. So we're gonna recompile our shaders and get it back to what we know it to be. And yeah, guys, that's my contribution to the world today. I don't really have much more to add about the hit shader for now. We have a lot of work to a lot of work in front of us to sort of get going. So we're back to normal. All right. So now you guys know. If you want to be able to do this stuff and work on this stuff on your own, tutorial number 1 installs the Vulkan API on your Windows-based machine with a Vulkan-capable GPU. If you want to be able to run this specific example, it has to be a ray tracing GPU. So for NVIDIA, it's RTX and above. I don't know about the other vendors. It has to be ray tracing capable. All right. All of these ray tracing examples, you have to have a Vulkan, a ray tracing capable GPU for it, right? So tutorial number 1 installs the Vulkan API. Tutorial number 15 installs all of these examples. I walk you through it with a video on how to do all of this stuff. Yeah. We have a lot of work ahead of us just to dissect this algorithm, but we will take our time and go through everything piece by piece. So the bottom level, right? So the bottom level is always the geometry, and the top level is always the instances. So we have multiple spheres and things like that, right? We have our shader binding table. Raygen miss hit, right? We focused on the hit shader, right? Descriptor sets, we have to do memory operations. You know how that goes, guys. We got to do memory operations. Top level binding 0 is top level acceleration structure. Binding 1 is ray tracing result image. Binding 2 is uniform data. I think that's more camera stuff. Binding 3 is scene vertex buffer, and binding 4 is scene index buffer. Right? Create the ray tracing pipeline. Similar bindings to the descriptor set stuff. Right, so this is a ray tracing shader group, and this is where we modify how deep we want to reflect stuff. Raygen shader. So you see, every time I compile, it's because I need to get to this SPV format, right? So I have to update, I have to compile the GLSL shaders, so it spits out this SPV format that the application reads and runs with. There is a way where you could skip the SPV step and skip that compilation process and like directly change values and do stuff at runtime, but I need time to dive into that process. But there's a way to do it, like especially for the recursion value, you could change it on the fly. Um, so we have the RGen, Regen SPV, we have the Miss SPV, and we have the Hit SPV. So um, right, okay, so every time I see UBO, I just think camera, but might be wrong. Right, so this recreation thing. So if I change the size of the window, if the window has been resized, we need to recreate the storage image and its descriptor, right? So we've kind of alluded to this in previous videos, but basically you modify the window that you're looking at, you're gonna have to redo the swap chain, redo everything. There is one process I know where you kill the current swap chain and you basically restart the swap chain. There is another process where you do dynamic swap chain changes, but that's a topic for a different day. But that's what this all this stuff is we got to get the swap chain. I do have a whiteboard that talks about the swap chain, so look at my previous videos. I do have the whiteboard that I go through the whole swap chain thing and how it works, right? And how it relates to what's presented to the screen. We have our command buffer. Dispatch ray tracing, copy ray trace output to swap chain image. So this is exactly what I cover in my whiteboard, because you got to take the ray traced output and put it into the swap chain queue and all that. Yeah, transition. So you basically you take a blank sheet of paper out of the queue, you do something, you draw on it, and then you put it back into the queue for it to be displayed on the monitor. Once it's displayed on the monitor, right, so you see it says transition swap chain image back for presentation. So roughly what this is right. So you have a set of blank sheets of paper lined up in a line, right? You take out one blank sheet of paper, you draw on it, right? So prepare ray tracing output image as transfer source, right? You draw on it. You take that sheet of paper with the drawing and you put it back into the queue. You present it to the screen. And then after you've presented to the screen, now you clear the slate again, so it's a blank sheet of paper, right? I have the whiteboard that talks about that, where you have a set of blank sheets of paper in a line. You pull out one of the sheets, you draw on it, you put it back into the line, you present it to the screen or the monitor, to your computer monitor, and then once it's presented, you clear the slate, right? You clear the sheet of paper, so it can be reused the next time around, right? Transition ray trace output image back to general layout, right? That's sort of how the swap chain stuff works. Yeah, ray tracing stuff. So, right, so this is our draw command, render. So what happens if I don't draw, you don't see anything. If I don't draw, you don't see anything. If I draw, you see stuff. All right? It's that simple. If I don't update uniform buffer, yeah, I can't do that. Sorry. Creates other problems, right? But notice how I could simply just not draw and the application runs fine. It's just that you won't see anything. And that's it. We're at 585 lines of code, guys. So anyway, we got our work set out for us, but now you see the real deal Holyfield. Shout out to the author of the script. We're working our way through the examples. You know the deal, guys. We got a lot of work ahead of us, but we're gonna hang around this guy for a while. I've been looking at some other stuff too. Nvidia actually launched some new products and things related to computer graphics that I want to maybe take a little detour at some point, and just investigate. But yeah, guys, that is ray tracing reflections for you. We always have to have our shaders, our hit shader, our mist shader, our ray gen shader. And remember, shaders are something you could have multiple shaders and slot them out as you want. So if you want different behavior in your scene, like for example, how we played around with this guy, if you want different shaders for different reasons or to do different things, you are able to easily do that because it's an external file. All right. So anyway, guys, if you want to join in tutorial number 1 and tutorial number 15, I have it linked down below. Just know that the reflections or the mirrored behavior is part of the hit shader that controls it. It's not a texture or something like that. It's simply you are playing around with the behavior of the rays that hit. And it's something about calculating the normal, right? So you have to calculate the normal before you shoot back out the ray that you received and the information in that ray that you received. All right. But that is my contribution for today. Thank you guys for watching. Tell your friends. If you know anyone that's artistically inclined, please have them follow along. Support the channel. You know the deal. Yeah. Goodbye.